Let's see if we can understand exponential functions a little bit better by looking at some of their graphs. To begin with, let's graph the function 2 raised to the power x. To graph this, we could begin by calculating a table of input-output values for this function. So, for example, if we plug in a number like -2 for the variable x here, then we're calculating 2 raised to the -2 power. And remember that a negative exponent can be interpreted as a reciprocal. So this is the same as 1 over 2 to the 2 power, which is, of course, just 1 over 4. So filling that in, we've started to produce our table of input-output values. And we can do that for several more values. If I plug in a -1 for x, 2 to the -1 is the same as 1/2. If I plug in a 0 for x, 2 to the 0, well, anything that we raise to the power 0, any positive number we raise to the power 0, will give us the value 1. So when we plug in a 0, we get out a 1. 2 to the 1 is 2. And 2 to the 2 is 4. Now we're just plugging in whole numbers here because they're easy to work with by hand, but you can plug in other values too. For example, you could plug in a fraction like 1/2. 1/2 for x, a 1/2 power, remember we think of a fractional power as a root. A 1/2 power is the same as a square root. And the square root of 2 is approximately 1.4. So we can evaluate 2 raised to any exponent, and if we do that and plot a bunch of points corresponding to those output values, we get a picture that looks like this. So for example, if I plug in a 0 for x, I'll get out a 1, and if we look at that as a point with x and y coordinates 0, 1, that's right here on this graph. Similarly, the point with x equals 1, y equals 2 is right here on the graph. And plugging in lots and lots of points will give us this entire curve. Now, notice something about the behavior. If we plug in some very large values for x, things that are over here, the graph is way up here. So plugging in large positive values is producing very large outputs from this function. On the other hand, if we plug in x values that are over here on the left side of the x-axis, those are large negative numbers, like -100. And those are producing outputs that are very small, close to 0. They're all down here. The curve gets closer and closer to the x-axis. And that's because we can think of these 2 raised to a negative number as a reciprocal. So 2 raised to a large negative number is like the reciprocal of 2 raised to a large positive number. And the reciprocal of a large positive number is a small positive number, a number close to 0. Now let's look at another example. Here's another exponential function, 0.5 raised to the x. We could go through the same procedure of calculating input-output values. So if I have 0.5 and I raise it to the -2 power, we can think of that first as a reciprocal, 1 divided by 0.5 squared. 0.5 is the same as is 1/2, and similarly 0.5 squared, which gives us 0.25, is the same as 1/4. Now if I take 1 and divide it by a 4th, I get 4. And so that's the first value for our input-output table. Filling in some more values like we did before, and remembering that we can plug in other values, not just whole numbers, leads us to a graph like this one. So when I plug in x equals 0 and get an output y equals 1, that's right here on the graph. When I plug in x equals 2, I get an output of 1/4, which is down here, a smaller output. And when I plug in -2, I get an output of 4, which is up here, a bigger output. So this graph's a little bit different than the one we looked at before. This time, when we plug in large positive values, we get small outputs, as seen over here. And when we plug in large negative values for x, we get large outputs, as seen over here. So what's the difference between the example we looked at before and the example we're looking at now? Well, it's the value of that base. If we have an exponential function of the form b to the x, it turns out if the base is greater than 1, then the exponential function will be increasing, like we saw with 2 to the x. If b is less than 1, then the exponential function will be decreasing, as we see in this picture. The outputs are getting smaller. We call that decreasing. And that was the behavior we saw with 0.5 to the x. Notice that this b value is less than 1, whereas this b value was greater than 1. And I also want to remind you one more time that we only consider positive values for the growth factor b. So really, we're only going to ever look at positive growth factors, and we're going to care typically whether that growth factor is greater than 1 or less than 1, so that we can identify whether the exponential function is increasing or decreasing as the inputs get larger. There's a special growth factor that is very important in mathematics, especially in calculus. It makes a lot of the formulas you learn in calculus much easier. And so that's when you use the growth factor known as E, or Euler's number. And it's a special number. It's kind of like pi, and also like pi, it has a decimal approximation that goes on forever and is non-repeating. So I can't write the whole decimal representation here. I can only write an approximation, so I've written the first 5 decimal places. E is approximately 2.71828, and it's very important, as I mentioned in calculus, and we'll see it in this course when we cover continuously compounded interest later on. Now, let's say we need to evaluate this. Because E is such an important number, it is available on most calculators, and I'm going to show you a simple way to evaluate E cubed on a TI calculator. It turns out there's a special number for evaluating powers of E. If you look carefully at this calculator, there's a button here, third row from the bottom on the left side, that says ln. We'll learn about that button later. Just above it, it has e raised to the x, and that's the sort of expression we're trying to calculate. So to get that feature, which on this calculator is colored in blue, we want to hit the blue second button, followed by that button, and we can see the calculator's setting it up for us to evaluate e raised to a power. So if I want e cubed, I'll just type in e to the 3, hit enter, and out we get 20.09 approximately. Let's go back and see how we could also graph a function like e to the x on the calculator. Now think about this. Before we graph it, e is the base. We're using a base of approximately 2.7. So how should we expect the graph to behave? Well, remember, what we really care about is whether that base is greater than 1 or less than 1. In this case, it's greater than 1, so we should expect to see a curve that's increasing. Let's take a look. If I plot by pressing y equals, and then type the function e to the x, again, I can get the e by typing second, and then the button that has e to the x above it as the second feature. And then I want to insert an x here, and to graph on this calculator, to do that, I hit the variable button here that says x, comma t, comma theta, comma n, and in this mode the calculator knows that I'm trying to graph a function, so I want an x. I can set a window, and let's use a smaller window. Let's say from -2 to 2 for x, and -2 to 2 for y, and graph with that, and sure enough we can see a curve that's increasing just as we expected.